Let's begin, as we always do, with Java. The Java language and libraries really emphasize the idea of runtime configuration to an extreme. Basically, if you're writing Java code and you're not using introspection and heavy abstraction and serialization and deserialization, you're just not thinking in the Java way. And that can lead to some things that are somewhat easy to mock, but are actually very powerful abstractions. The code below is some code that I stole out of an application that's an open source application in Java. But you can see what's happening. Frame, set frame center property, abstract frame property manager, get frame property manager. We actually have to go get the frame property manager, and then from that we can get the property factory, and then we can make a new property using a JSON property, and we do that from the loaded properties that we've assumed loaded somewhere else, and we look for frame centered. I've X'd out the name of the organization from which this comes, and that then sets the whole frame to be centered. Okay, fine. I mean, that's a way of doing it. That gives you a lot of flexibility, right? I could have a different property manager. I could have a different factory for properties. I can replace all of these components, and the application can work very differently, and that's a lot of flexibility, and that can be great. Let's talk about the Java naming and directory interface. So what is that? Well, it's a common interface for naming and directory services. What's a naming and directory service? I know what all those words mean, but what do they mean when you put them together? Well, it's a service, something that provides information to you for naming and directories, like DNS. You go to DNS and you give it something like tntech.edu, and it gives you back something for that name, like an IP address. Okay, so that's what DNS does. Corba is a little different. It lets you serialize and deserialize objects. Common object request broker. I forget what the A is for. Who knows? Could be anything. I'm going to say it's for Antelope. So you reach out to Corba and you say, I want to call a property on this remote object, and it will do that and give you back the result. LDAP, the Lightweight Directory Access Protocol, is a way of storing enterprise-wide information and then making it available. And that's great. That means I can write an application that I can run on any computer in my enterprise, and I give it an LDAP address, and it's able to then reach out to that remote LDAP repository and pull down the information it needs. And I can do authentication, and I can serve out application defaults, and tons of other stuff through that, and it's very handy. I maintain it in one place, and then the results are pushed out everywhere. And clearly, if I'm writing a Java application, I would like to have access to this kind of stuff. And so you can see the stack over here on the side. Here's my Java application. I talk to the JNDI API, Java Naming and Directory Interface. That talks to some naming manager, something, somewhere, which talks to the JNDI SPI. It's all acronyms all the way down. That then can talk to LDAP or DNS or NIS or NDS or RMI or Corba, or many others. And then those all talk on the Internet of Very Safe Things and give you back a result. And here's a concrete example, right? It's good to have actual code to look at for this. And this code, as you can see up here, that comes from Oracle, who is the company that owns and maintains Java. It's from a tutorial on LDAP, and here you go. You can go look this up, and you can see what's happening here. I set up an environment for an initial context. I make a hash table. Initial size 11. I then put in there some information. Initial context factory is the LDAP context factory, which breaks the usual Java rule of not abbreviating things. There's CTX there, but what are you going to do? And it breaks the other Java rule of usually when you have an acronym, it's all uppercase, but here it's mixed case. That's okay. the provider URL, okay, well that's going to be on localhost. I mean, that seems fine. I asked to use colon as the encoding character. I do some other stuff. I set up that I create a new fruit, an orange, and then look at this. Within the context, I bind CN favorite to fruit. If you're not familiar with this kind of thing, that's what LDAP looks like. Okay? And then later I can look it up, and that will give me back a fruit, and I cast it to a fruit, and I can print it out, and I can do other stuff like that. So this is a way for me to bind it up in a potentially remote database. In this case, I'm using one on the local host, but I could use it on a remote machine, and then I can access properties of it later, and it will do stuff. Let's talk about log4j. So lots of applications need to write out information as they run. It's very common, right? Something goes wrong. Maybe you need to log that information so you can provide support to the customer later, or you can debug it, or so on. Or maybe you just want to be able to write error messages, and you want a consistent way to write error messages. So you should be using a logging framework. So log4j is a very extensible and very flexible logging framework. It's used by all kinds of Java projects. Some people like to just populate their code with system out println with static strings. That's a bad practice. It's bad. If you need to change that or modify that, you've got these printlns all over your code. It's messy. It's a problem. It's difficult to deal with, and it doesn't scale well. Log4j, using a logging framework, whatever it may be, can really help, because now you have a consistent way of producing logs, and you can actually specify that those logs maybe go to a file, maybe some of them go to the console, maybe some of them go to a sim, and get recorded for use later to diagnose problems. Who knows? They go to some simple event manager. So you should use a logging framework. I'm encouraging you to use a logging framework. You should. And so a couple years back, somebody looked around and they said, hey, JNDI is awesome. Because I can go and get stuff out of my LDAP database and use it. And log4j is awesome because I have this nice logging framework. It would be great if I could use stuff that I refer to remotely using JNDI, if I could use that to configure my logging framework. That'd be awesome. Let's bring together, it's like peanut butter and chocolate, right? Bring together the Java naming and directory interface with log4j. I would like it if log4j supported JNDI lookup. And you see currently lookup plugins don't support JNDI resources. It would be convenient to support it. It's easy, and please do this. And request for a new feature, it actually had a major priority, and you see over here fixed, closed, and it's put out there. And in fact, if you want to go see the code for the patch, it's right here. Submitted, we're good to go. That happened back in 2013. And here are the comments from 2013. Hi, I just attached a patch to provide built-in JNDI resource lookup with unit tests. Please take a review. Cheers. Your patch was committed in revision such and such. Please verify and close. Thank you so much, Ralph. I appreciate for the site documentation as well. Cheers. Everyone is happy. You can now use JNDI directly from log4j. The world is beautiful. Everything is happy. And then for some reason, in 2021, in December, someone comes along and says, nice work, with a little snarky face. What could that be about? What could that possibly be about? Well, here's how this gets exposed in log4j. I have a logger, which is an instance of a class, an object created by log4j, and I'm going to write, let's say, an info message. There are different levels of message: error, debug, info, so on. And I say I'm running with home set to, and look at this, I can pull in an environment variable like home and say where that is. That's awesome, right? It's awesome. I could say running with secret key and give you the secret key. That's cool-ish, I guess, probably. Or I could say searching for string, and here I do some interpolation, these little brackets, and what I put in there is this. And look at this. It's a JNDI call out to an LDAP server. It's going to use the LDAP protocol to talk to my server and go get the object. So here we use JNDI to refer to an object in some server which we retrieved and loaded into the running VM, and then it gets executed. So what's happening is we use the Java naming and directory interface to connect to the LDAP server and obtain this object, this blob of Java bytecode. And we load it, and then we invoke a method on it to produce a string, because that's how that works. So we're running some code from an object we just grabbed. And methods in our object can do anything, and it's now code running in the same VM. And in case you hadn't already guessed it from above, exposing environment variables was also not maybe a great idea. But how do we use this? Well, we exploit this in a very similar way to SQL injection. For instance, I give you a search string, and the thing I'm looking for just happens to be this string right here with the curly brackets and the $sign, and when it gets substituted in and it gets logged as the query, assuming we log our queries, if we log that query, Log4j is going to see this and it's going to interpret it. And that's where the mischief happens. And then we have taken some code, stored, possibly on some malicious site remotely, loaded it into the running VM and executed it. That's literally remote code execution, which, as we all should know by now, is a bad thing. And this was, in fact, a bad thing. So here you go. You go to the Adobe homepage these days, and very loud, violent text greets you about the security vulnerability. And you see the CVE number right here that you can look up on the National Vulnerability Database, the NVD, if you want. And the summary is Apache's Log4j2 vulnerability to remote code execution via the JDBC appender when attacker controls configuration. So if the attacker can give you a configuration and you then do the appropriate query for it, this is going to be bad. Log4j versions 2.0 through 2.17, including the security fixes, are all vulnerable to remote code execution when an attacker with permission to modify the logging configuration can construct a malicious configuration using a JDBC appender with a data source referencing that all sounds like a lot of work, right? There's a lot of work going on to exploit this. But in reality, if you've got like a query string where you can type that in, that may be all you need to do. You don't need to control all this other stuff, right? They add all this stuff to make it sound like it's hard. It's probably not going to be that hard. The answer is to upgrade to the newest Log4j and refer to the security page for other information. And you'll see that it spawned a whole bunch of other ones as well, additional CVEs, because once you have this substitution where you then expand it into something where you're pulling something down from a potentially untrusted site, there's going to be a whole raft of other vulnerabilities that are associated with that. Once you've discovered one, you're going to then mine around to look for others, right? Once you find the one gold nugget, you're going to assume a gold vein is nearby, and you're going to look for that gold vein in the mine. Is it the worst vulnerability ever? It actually might be. Minecraft servers were vulnerable, and when your Minecraft servers are vulnerable, that's terrible, right? And so you may be thinking, well, I wrote some Java code, but I didn't use Log4j, so I'm safe. I'm safe because I didn't actually use it. And that brings us to the real point of discussing this vulnerability, the prevalence in Java projects. So you can see, this is a little graph. When they surveyed stuff that was out there, surveyed stuff on GitHub and GitLab and these other sites, they found that about 40% of the projects directly reference log4j. Wow, there you go. Those are the ones that are vulnerable to this vulnerability, except the others. There's another 60% of the projects they surveyed, which were vulnerable to it, were vulnerable because they used log4j indirectly. This sums to 100 because they only looked at log4j use in projects. And of the ones that use log4j, 40% of them basically used it directly. The other 60% used it and may not have known they were using it because they were using a library that used a library that maybe used another library that used it. And that gets us to this whole issue of direct versus indirect dependency. And again, same paper, they take a look at direct and indirect dependencies. Okay, and so in blue, you see direct dependencies, and in orange, you see indirect dependencies for the projects that they surveyed and vulnerabilities. And so for this guy, you see mostly it's direct dependencies. But over here we get to node, and it's only 14% direct, and the rest is the tons and tons of other libraries you are including that provide you with the vulnerabilities. So there you go. You can also have a look at how someone on YouTube would explain this. They would explain it differently. There's a video that you are welcome to watch to see how someone on YouTube explains it.
Okay.
What if we knew about this back in 2016 before all this started? And someone tried to warn us. That would have been great if someone could have warned us years ago before the bad things happened. In fact, they did. Do not perform JNDI lookups with untrusted data. This was given in Black Hat in 2016. Right? It's already in log4j at this point, but you know, if they were watching this, they may not have thought it was that important. All right. So what's the point? The point is, even if your code doesn't use log4j, it might use code that uses code, etc., that does, and you can still end up being vulnerable. How do you defend against this kind of vulnerability in your code? And can you? How would you know to defend against it if you're not using it, but you're including a library that includes a library that does, in fact, use it? That's the challenge. Okay, so there are some attempts to solve this problem. Rust, for example, has a means of auditing your code for known security problems. So if you're using a library that has a vulnerability posted against it, then Rust can examine all the libraries you're including and then warn you about that one. And that's kind of handy, right? But again, you have to know about the vulnerability. Okay, let's talk about security at the edges of your application. Security is not like many of the other properties you may have talked about. It's not like reliability. It's not like availability, usability. It's something a little different, and that's going to be my argument, try to explain why it's different. A system can be reliable against random attacks. Okay? And it could even be resilient to them, right? A small rock hits your windshield and it bounces off because they just don't have enough energy to penetrate the windshield. But if all of a sudden 1,000 small rocks come at your windshield in more or less the same place, maybe they break your windshield. Okay, they're not resilient against a systematic kind of attack. And attacks in the cyber realm are in fact systematic. A conscious, intelligent person on the other side, maybe, is organizing things to try to overwhelm your security. And you may be just fine against randomness, but you're not fine against that kind of systematic attack. Security is invisible and hard to measure. Is the computer I'm using right now, does it have malware on it? the malware light's not on, so no. I don't know. Right? It's not. Nothing is reported to me there's malware on it. But again, the security property in this case is invisible. I don't necessarily know. I just know that nothing is telling me that it does have a problem. Security is highly contextual. If I can put one thing in your head, and maybe one thing only, it would be that security is contextual. I could take a system that's built in one environment, deliver it to a different environment, and it might be perfectly secure and great for that first environment, but the second environment has some properties that I haven't accounted for, and it breaks. Right? I can take secure code off one computer, put it on another, and maybe on that machine things are a little different, and it breaks. I put it in a different environment, even an environment that just has different security policies, and suddenly that system is not secure because the security policies create an environment where it doesn't work the way I intended it to. A good example of that's passwords. Right? Passwords can be very secure. These are very complex, long password. Some places have very restrictive password policies. Anyone who works at Oak Ridge, I'm not saying anything about Oak Ridge. I'm just saying that some places have highly restricted password policies that take the large space of potential passwords and shrink it down to a fairly small space. And that can be bad. That changes the security of a system that uses passwords by imposing this policy constraint around it. Security is a property of systems. You may think, well, that's obvious. Of course it's a property of systems. A system is secure, it's not secure. But you're probably thinking about a particular system without thinking about the fact that components of it are systems in their own right, and the system you're thinking about is a component in a larger system. Healthcare. Security is a property, let's say, of a healthcare system, and you're probably thinking software that runs on a computer in a hospital. But that is also part of sort of a health delivery system, right? There are nurses, there are other computers, there are devices like infusion pumps, there are hospital policies. All these things surround it and create a larger system. And the software is just one piece of that. And the larger system might be secure or not secure. And then the components, you have to think about whether they are secure or not secure. And that can include components of the components all the way down. Okay? Security is a property of systems, and it's all systems all the way down and all the way up. And that leads us to the next point, which is I take two secure systems that I know they're secure, and I plug them together. Okay? Is the result secure in the same way the individual systems were secure? Could be, but it also might not be. It turns out composition is an unsolved problem in security, and that's important, right? I need to think about what it means. And one of the reasons why it's problematic is you think about composing small systems to create a bigger system. Each one of those probably has a responsibility assignment. The right way to think about a module in a program is to think of the responsibility assignment for that module. And it does its job, and it does it securely, and it does it efficiently, and it does it correctly. And I take two of those and I plug them together. But because I plug them together and they communicate data, that communication channel might suddenly become vulnerable. Or one might use data in a way that while it's secure for that application, is not secure for the composition. Security is often binary, and what I mean is either a system is secure or it's not. Security doesn't gracefully degrade the way reliability might. Right? I start loading up. I got my computer on. It's running. I load up, let's say, Minecraft. And my computer's ticking along. It's doing fine. It's a little slower, but it's doing fine. And then I turn on shaders. Oh, it's a little slower now. And I load up some really fancy shaders, and now it's really slow. The performance of my computer is sort of gracefully degrading under load. Security is not like that, right? Once you've broken security in one way, you may be able to leverage that to break security in every way. And That's a problem. Security is often an assumed property. We act as though systems are secure. Maybe they are. Maybe they're not. Again, it's invisible. How do you know? But we'll act as if they are. You buy software or you download software from a site and you say, yeah, okay, I'm going to run this. And it says I need to escalate privileges in order to install some new codecs on your system. You're like, yeah, go ahead and do that. You do that. It downloads some stuff and installs it and you're good. Or you're building a piece of software, let's say for a class, and it says, hey, to build this, I need to download all these libraries. And you say, sure, go ahead and do that. And you download them and install them. And you elevate privilege to do that, and life is good. Right? I mean, we do that all the time. So we download a game. It says I've got to install this stuff, install it, and it has to escalate privileges to install some graphics drivers. And then we want to download a patch someone's made to it. And the patch is going to, of course, make some changes to the graphics driver, so it has to escalate privilege too. And now there's all this code that's sort of unvetted and untrusted on the computer. But we still make the assumption that, oh, this is fine. I'm sure it's fine. SolarWinds attack is an example of this. People assumed SolarWinds, a security company, I'm going to download software from their site and put it on my machine. It's security company, security software. It's secure. But in fact, the software that was up there for download had vulnerabilities. Or actually, not vulnerabilities. Apologies. It had actual malware present in it. And security degrades. I said it didn't degrade gracefully. And I think you know what I meant by that. What I mean by security degrades is, I mean that over time. A device that is secure against all attacks today may be vulnerable tomorrow because a new known attack is discovered. Okay? Or I update the software, and the updated software contains a new vulnerability, right? Everything is fine. Log4j is ticking around in my system. Everybody's happy. I update to the newest version of Log4j with its security patches and all of that, and suddenly I'm completely vulnerable because it includes the ability to reach out to these remote sites and execute remote code. Those are the things that I think make security different. Sorry I took a long time on that, but I think it's important. I want to emphasize that notion that there are systems of systems of systems of systems. And so let's think about the things that are present in there. So here we have the software layer. That's where we like to sort of think of the world. And we like to think about the software we're building. We're building software for a particular purpose, and that usually requires that we use some other libraries. And so we have software with known vulnerabilities that we attach to us because we need to use it. And we have unrelated software that we also attach to it. It's, if you statically link a C executable, you might wind up with lots of stuff in there that you don't need or use because you're having to statically link an entire library in there that contains a lot of stuff that you don't need or use, but it's in there nonetheless, and maybe someone can find a way to exploit and use that. In addition, there's operating systems. There's other unrelated software on the machine. Maybe you can find a way to use some of that. Maybe there's a compiler on the machine, or there's debuggers on the machine, and I can run them as you, and I can run them with your software, and I can do that, let's say, from a script that I don't need to be privileged to run, and I can rebuild something so I can sneak my code into your system and then wait around and eventually gain privilege. There you go. And maybe I build some boundaries here. So I authenticate users. Here's some people. Here's a suspect person, possibly malicious. And so maybe I authenticate them. And I have let's say a boundary down here, right? So I have the software here, but the machine has some protection stuff. It provides some hardware for the particular purpose at hand, and it provides a lot of other hardware that maybe I'm not using, right? Maybe I'm using the drives and the speakers and a bunch of other stuff, but I'm not using the USB interface, and it's got a CD-ROM drive from 1992 in it, which has some bad vulnerabilities in the firmware that maybe I can exploit. Who knows? And then all that sits on top of the fundamental physics And that can sometimes be exploited, and we'll actually give an example of that later on. But here's my stack. I try to sort of partition stuff up. My partitions are not beautiful. The operating system tries to partition things, but at the lowest level, there may be stuff that has to be shared, and that may be a way for me to get from bad software over into the good stuff. Okay? So sometimes there's ways to go around a particular piece of protection. Okay. We don't know how to compose systems to guarantee security, and an adversary is going to exploit vulnerabilities wherever they can find them. Once you've solved a problem, the next thing to do is to compose it with solutions to unrelated problems and share resources. That's what a computer does. That's what your program on the computer is basically doing. I didn't mention it explicitly in here, but I mentioned it before. Up at the top, policies and procedures. You get everything right in here, and then you add some terrible policies on top, and your whole system is now insecure. It can happen. Vulnerabilities typically occur where two systems touch, because there is information flow, there's an interface, there's a protocol, and that could be, it's obvious that sort of there are APIs in here that we're using, but in addition, there's an interface with the person, there's interfaces with the procedures, there's interfaces with the fundamental physics. All of those provide a place where you can go and look for vulnerabilities. And in particular, industrial control systems, ICS systems, have multiple boundaries, and they can have different security postures. And those interfaces are especially places where you might want to poke and prod. If you're building software for that kind of an environment, you need to be very explicit about what information crosses that boundary, the state that it's in when it crosses the boundary. Is it encrypted? Is it not encrypted? And what guarantees you make about it, and what guarantees you make about information that you can make about information that you're reading in, right? So I'm taking in a request. Maybe I should check all the parameters of that request to be sure it's properly formed before I try to execute it. Okay. It's like input sanitization in PHP. So, up at the top, your application. Your application is awesome. You understand it, and it's secure. And then you attach log4j to that. You use the library, but you limit its use to just a few methods, and you trust it, but not as much as you trust code you wrote. And then it's using JNDI, and you have no clue this even exists. So when you look at your code, you're looking at these two components maybe, and to you, everything looks fine. There's no exploitable vulnerability. Nothing is wrong. All the code is working correctly as designed, and there is no bug. But there is still a vulnerability. It's people who think of vulnerabilities and weaknesses as bugs, I think are thinking of it incorrectly. You can add a feature to a secure system and wind up with an insecure system. This video is a wonderful example of it. It's a little long. I forget exactly how long it is, but it's great. This fellow, I think I've maybe posted videos from him before. He did the fuzzing of the x86, which is wonderful stuff. He found an x86 chip which had another processor in it, and he was able to leverage that processor to backdoor the first and break all the security in the operating system. And that's really, really neat, and his explanation is pretty good. If you get time, you should listen to it.
Good afternoon.
One way to think about security is to consider it to be a set of guarantees. Okay? So in some ideal case, there would be theorems you could prove about your system, and those theorems, once proven, they would be universally forever true, and you would know that your system was secure. That would be great if we could do that. My argument is we can't do that, and we can't do it for a number of reasons. The most important one is systems don't stay static, right? You may be just fine for the world that you're defining today, but you port it to a new future architecture, and now it's not secure anymore. So let's try an attempt at a definition that uses that. We'll say a program P is secure if and only if, given that program P performs action A, we can conclude that action A was requested by an authorized user U. So let's try to puzzle this through for a few moments. When is program P secure? Well, it is secure when, right, a necessary condition for it is whenever it performs a particular action, that action was requested by an authorized user. So we see that your garage door goes up, and it's a computer-controlled garage door. And it goes up because a relay was tripped. The relay was tripped because it was requested by an authorized user. So if the garage door is going up, we know it was requested by an authorized user, and that gives us security. And when I assert something is secure, I am asserting that that is true. That's what it means. It means that that's the only time that happens. Seems like a pretty good definition. Are there problems with it? So I would advise you to think about this. Think about the fact that there's sort of an if-then in that second part, and what that might mean and how that might work. We want to think about different definitions of security and try to figure out what they might be. Defining security is hard. Can we use the definition I just gave you to conclude that a program using log4j, the vulnerable version, is not secure? Program is secure if given it performs an action, that action was requested. It downloaded code remotely and executed it on the machine. That's one way to think of it, right? I didn't request that. Did I? Maybe I did. As an authorized user, I may have entered something into a search field that caused that to happen because that was my intent, and I'm authorized. Does that mean it's secure or insecure? What does that exactly mean? So think about those sorts of things. All right. Let's talk about weaknesses and vulnerabilities and exploits and how those all fit together. An exploit is a program or a piece of code designed to find and take advantage of a security flaw or vulnerability in an application or computer system, typically for malicious purposes, maybe always from, I don't know, maybe not. This is just installing malware. An exploit is not the malware itself, but the method used to exploit and evade security. So there you go. If you want to see how these things work, there's a good video here that's showing getting a reverse shell using a malicious DLL, and you can go take a look at that. Metasploit is a tool for doing exploit stuff, and if you're not familiar with Metasploit, you might want to get familiar with it. So this is one definition of exploit. It's one from Cisco. We're going to give different definitions as the course goes on, because of course this doesn't cover exploiting physical systems. It doesn't cover exploiting multiple things together. And it explicitly says, I'm going to find a security flaw in an application and take advantage of that. That's pretty good. I think, again, it's a pretty good definition, but I think we may be able to do better later. And so one of the questions I want to ask is, does the exploit have to be code? What about a malicious configuration file? Right? If I can modify your bash RC, that's good enough, right? I'm doing good. If I can modify INI files on Windows, that's probably good enough. I can probably get really far with some of that. What about modifying a physical sensor? Right? Maybe I can get to some persistent settings in a sensor somewhere, and I can change the set point. And that causes a system to behave differently, and maybe that's good, right? Are those all in scope? And I would argue that for security, yes, they are. for secure software development? Maybe. It depends what you're trying to do, right? Maybe I should be verifying sensor settings, verifying configuration files in some way before I take them for granted. An exploit is a method, inputs, environment settings, or combinations that results in a system performing an action that violates a security guarantee. That's my definition, or that's the definition I'm presenting to you here. It's some method, something, I do something, and that something that I do results in the system performing an action that violates some security guarantee, and that presumes that I know what the security guarantees even are. Okay, all right. A vulnerability? According to the CVE, a vulnerability is a weakness in the computational logic, it's fancy words for code, found in software and hardware components that when exploited results in a negative impact to CIA confidentiality, integrity, or availability. We'll actually talk a little more about the CIA triangle in the future. Mitigation of vulnerabilities in this context involves coding changes, but could also include specification changes, or even specification deprecations, removal of protocols. How do I fix Log4j? Maybe I take that thing out of Log4j. Right? I change the specification. It was behaving correctly, and maybe I have to take that out because it's a fundamentally insecure feature. Over on the right-hand side is some code that, as you can tell from the top, is a trivial buffer overflow vulnerability. You should take this code, you should put it on you should copy it out, paste it into a file, compile it with the C compiler, and play with it and see what happens. Some compilers may complain to you about parts of this code, and that's a hint as to where the vulnerability is. They may complain to you at compile time. Sometimes you'll get a complaint at runtime, and that may hint to you what the vulnerability is. But you can compile this and then actually, without knowing the true password, be able to get that authorized prompt at the end to come up. So you type a password, it tells you it's the wrong password, but it still says you're authorized, and that's because of a buffer overflow. And you should understand how this basic thing works and why this code is bad, insecure code. So I said CVE on the previous slide. The CVE is the common vulnerabilities and exposures. I'll probably say common vulnerability enumeration many times. Forgive me, common vulnerabilities and exposures. That's what it actually is. It's a MITRE developed standard for vulnerabilities. Why do we need one? Well, you might say that vulnerability where you put a negative value in the field, and that causes this thing to allocate the wrong number of bytes, and then this happens. This way, you can just say CVE 2017-2192, and you can look that up, and you know what it is. And people who are providing software can say, yep, that vulnerability affected us, and we fixed it. You can search their site and find that CVE, and you know it's there, and it's being addressed. It gives you a well-known universal name for that particular vulnerability, and that's great. It says it improves over everyone giving the vulnerability their own name, and that's what it does. Okay, so you're saying, I like your explanation of it, but I need a corporate mission-centric overview of an organizational vision, etc. Click on the overview on the right-hand side, and you can have that and have at it. The Common Vulnerability Scoring System, the CVSS, is a way for us to assign a number to a vulnerability to basically say how bad it is. And I would argue that there are some important things that this badness measure misses. Now, let's say you found a vulnerability in your system. You can go over to the NIST site and use the calculator to figure out the score based on what you know. You can put this information in, you say, I think this is true and this is true, and get a score for it. And some organizations actually do that, and then they'll fix the ones that end up having the highest. They sort of rank them by highest to lowest score, and they'll fix the higher ones earlier. Okay? But this is just a way of putting a number on it. Is it ideal? No. And I would argue that one of the fundamental things that's missed in here is persistence. So, sing the praises of Apple for just a minute, if you can bear with me. One of the neat things about the iPhone is it's such a walled garden that even if bad stuff gets on your iPhone, you can mostly get rid of it by rebooting. It's very hard for it to get into a state where it's persistent. It's easier on Android. Not saying one's better than the other. I'm just saying that's one of the properties of it. Persistence is something that can be really troubling, right? Something that I can just reboot my computer and it's gone. Fine. I can delete some files and it's gone. Fine. If I have to reflash the BIOS, that's much more serious, and that's not accounted for in these metrics. So I'm just pointing out that I don't think these metrics are perfect, but they're good. They're, better than anything I invented and made public. The original Log4j vulnerability has scored a perfect 10 on here, and you can look it up. There's its CVE number. And you can go to the National Vulnerability Database, and there's its address. So you can use the CVE designation to look up stuff, and that's great. You can see what's affected it, you can find out more about it, and you can see if it's been patched. The important part is the existence of an exploit implies the existence of a vulnerability, and the reverse of that is true too. If you have a vulnerability, that means there is an exploit, right? It's not enough to just have a vulnerability. You can't have a vulnerability without an exploit, right? It's not vulnerable. It's just a weakness. The exploit need not have been observed in the wild, but it must exist. A security researcher may have come to you and said, here's some code that causes a bad thing to happen. You're like, oh, well, that's the exploit. And then it's using a vulnerability, and I'll add it to the CVE. How do we prevent vulnerabilities from getting in programs in the first place? Secure programming class. We should be thinking about that a little bit. Graduate secure programming class, I would point out. So I'm not going to tell you how to write secure code. My goal is to get you to think about security, think about it from the point of view of what these things mean, and have a security mindset with whatever you do. Right? You learned to write code when you were an undergrad. So how do we prevent vulnerabilities in the programs? Well, we need something to look for, or we can scan a program, or we can test it in a certain way that will reveal that there's something bad. And a piece of code by itself might not be vulnerable, but it may become vulnerable or become part of a vulnerability in certain contexts or in combination with other code. And again, that was illustrated by the Log4j example earlier. Right? Single lines of code are just fine. It's when they gang up on you that you have the problem. A weakness. A weakness is a flaw or a fault or a bug or some other error in software or hardware implementation, code design, or architecture that, if left unaddressed, could result in systems, networks, or hardware being vulnerable to attack. I kind of like this definition because it's very inclusive. It's very inclusive. A flaw, a fault, a bug, or some other error. But, it could also just be the way things work, right? And what you have is the context around it makes it vulnerable, right? If you look at the picture, there's nothing wrong with that arm. The arm there it's fine. It functions correctly, I assume. You drive up to it and swipe your card or whatever, and the arm goes up and it comes back down. Nothing is wrong with any of that. It's performing exactly fine. The road's there. The road's not wrong. There's another problem, and that problem is the context in which that arm and the road are placed that allows for a weakness and then, as you can see, a vulnerability and even an exploit. And we note that the scope here is expanded to include hardware and architecture, which I love, right? I love that because if you're a bad guy and you want to exploit a system, you don't care how you get there, right? You don't care how you get there as long as you can achieve the effect you want, right? You are Very much results oriented, and whatever gets you that result, that's what you do. And in fact, there's a common weakness in enumeration, which is why I'm going to say common vulnerability in enumeration until the day I die, even though that's not the right thing, because enumeration gets stuck in my head. Weaknesses, just like vulnerabilities, can be cataloged, and in fact, someone has done that, and that someone is, of course, obviously MITRE, because this is the thing that MITRE wants to, this is the hill they want to die on. So MITRE created the common weakness in enumeration to capture all of these common patterns in code that result in weakness. And I said code, but it could also be, there's also hardware and there's architecture, and all of that is in fact captured in here. There are pieces of this that have to do with circuit logic, with power, with clocks, with glitching. All of that are in here. And the idea is that we could then develop tools that can look for these weaknesses until we can eliminate them once and for all, and that's really powerful. Over on the right, you see an example of one, CW1232, which happens in this case to be improper lock behavior after power state transition. And we have a system that has a locked and unlocked state, let's say, and I turn the power off and I turn it back on, and I now don't know the status of the lock, but I make an assumption about it. And so you can see register lock bit protection disables changes system configuration once the bit is set. Some of the protected registers or lock bits become programmable after power transitions. There's a whole description of it in here, and it's one of a class of different problems. And then it could be because of software, it could be because of the way hardware works. Here are the top 25 weaknesses as per MITRE. Number 1, out of bounds write. Right, that's your buffer overflow, what have you. You see at number 9, one of the favorites, cross-site request forgery, and you'll find that on the OWASP top weaknesses as well. If you're familiar with OWASP, there's many of these catalogs, and if you're a web programmer, OWASP is one that you know about. 7 is use after free. 21 is server-side request forgery. All the big hits are in here, and you can see that they don't change much from year to year because people make the same mistakes. All right. Whew. So there's homework. It's due on the 30th. And that homework is for you to give me a definition of security. Think about what you would like to prove about a program in order to say that it's secure. Right? So you write this code, and you can give me the context for which you're writing it. But I want you to think, what would it mean for this to be secure in this context? And what would that be? So tell me the context, and then tell me what your definition of security would be. And you should think about, can I check this? What's necessary to check it? And if it can't be checked, an interesting question would be, is there something else that could be checked? Right? Does it point to something else that's sort of a secondary effect that I could look for? Right? A good formal definition of security might be a good formal definition of security, perfectly reasonable. We all agree with it and love it, but it's not the kind of thing that is practical in terms of checking, and that could be true. Or maybe you have one that's super practical in terms of being able to systematically check it, but it turns out that the time required to do that work is hundreds of years. It doesn't matter. Come up with the definition that you like and then submit that.